of course, I'm very happy to talk about this topic, which is, in some sense, at the crossroads of many topics. And I got interested in this topic because in relation to what I'm doing now, and we will see it at the very end of my talk. So the topic is Quintics, Platonic solids, and Rogers-Ramanujan identities. And I hope that I will have enough time to explain the relationship between those topics. So, algebraic equations, as we know, are a very nice box where old and new mathematics can be combined. And in my topic, two numbers will play a fundamental role: 5, the number 5, and the golden number 5 equal to 1 plus 2 to 5 divided by 2. And of course, the first 5 is algebraic 5, and the 5 inside the golden number is more geometric. So the history of algebraic equation, we know that the quadratic equation is as old as maybe the human existence, but the cubic equation has more recent history, and we see here some date around 1515. Fermat found a solution, but he didn't publish it. And the solution was rediscovered in 1535 by Fontana, and the nickname is Tartaglia. And I have to say, Tartaglia. And I have to say that in all my linear algebra classes, I give to my students the poem of Tartaglia, explaining how to solve the cubic equation by following the line of the poem, but the Italian used there is a little bit complicated. So, yeah. But the tragedy of this story is that Cardano published this proof, and of course, Tartaglia was not happy with that. And if we use, and the formula that we have here is what we call now Cardano formula. And this Cardano formula gives the roots in terms of cubic roots of some expression, depending on the coefficient of the coefficient. I didn't give here the P and Q, but the idea is to take this x3 plus x2 plus bx plus c equal to 0, and then to reduce it to the canonical form, which is x3 plus px plus q, up to by some translation of the variable. And in the canonical form, the p and the q are used to give the three equations. And if you take this small example, x3 plus 3x plus minus 4 equal to 0, it has the trivial root x equal to 1, which is unique real roots. And if we apply Cardano method, you find this. And then we have to solve this small problem that one is given by cubic root of this expression minus the cubic root of this other expression. This is a good exercise for cubic roots. And then after this, we have the quantic equation, and Ferrari gave a method, but and in 1799, the fifth equation was solved by Ruffini, but there is a gap in the proof. So at the end of the 18th century, we have the problem to find a solution of the quintic, because the method of refuting contains a gap. And then Abel published at his own expense a proof in 1824, and he says that the general quintic can be solved by using the classical operation, addition, subtraction, multiplication, and division, and taking square roots. And when he published this paper, his proof in 1824, Galois was only 13, which means that Abel didn't use Galois theory in his proof. And the Galois gave finally the proof in 1824, and his paper was rejected by the French Academy of Science. And as we know, Galois passed away at the age of 20. He didn't see his paper published because the paper was published only in 1846. So this is, and I would like just to, as motivation of the coming topic in my talk, to consider a very particular quintic equation. X5 means x plus some constant gamma, and this solution given by a series in powers of gamma due to Lambert and Eisenstein, and this series is not very quickly convergent. So, but the main point here is that if we look at the coefficient, this coefficient can be put in some general form. You have the combinatorial coefficient pk over k, and then we have 1 over p minus 1 k plus 1. And if you take p equal to 5, then we obtain the coefficient that I gave in the power series expression of the solution. These coefficients here have very nice particular case, is when we take p equal to 2, then we obtain the Catalan number. The Catalan numbers are very important. They are related to graph theory. And at the end of my talk, we will see another relation of the quintic to graph theory. In any case, those Catalan numbers are, the Catalan number is the number of the staircases, of the number of paths going from the origin 0, 0 to the point n by just taking this kind of red paths without touching the line y equal to x. So this is a good interpretation, and this is our first, we meet graph theory here. So what is important in the quintic is the Platonic solids. Here we have the Platonic solids, and the Platonic solids we have 5. This is a theorem. There is only 5 Platonic solids, and we will be interested in the more enigmatic one is the itohedron. And we can see that in the Platonic solid, we have the relation, the Euler relation, that the number of vertices minus the number of the edges plus the number of faces is always equal to 2. There is, this is universal relation, but we have also another relation. If you take, for instance, the tetrahedron, and if you look, so all my Platonic solids here, the tetrahedron here, the faces are always considered supposed to be equilateral. And then if you go from the center of one face, if you look at the center of the face and you connect the centers, you get another tetrahedron. I will say this, that the tetrahedron is its own dual. By this construction, taking the center, connecting the centers, we obtain another solid, and this solid is the tetrahedron. It is its own dual. If you take, for instance, the cube, and then you do the same operation, you obtain the octahedron. And if you take the octahedron and you do the same operation, taking the centers, connecting the centers, you obtain the cube. So the cube and the octahedron are dual each other. And if you take the decahedron and you do the same construction, you obtain the icosahedron. And if you take the hexahedron and you do the same construction, you obtain the dodecahedron. So we have 5 Platonic solids. One is its own dual, and the others are 2 by 2 duals. And now here we arrive to the golden number. Let me just put a small picture here. So I want to. So let's do it by hand. So I take a right angle triangle. And this side is 1/2. This side is 1. And then I take this side, of course, is root of 5 divided by 2. And then if I take this side and I put it horizontally, I arrive here. So this is the geometric construction of the golden number, 5, 1 plus root of 5 divided by 2. And in all my talk, what I call golden rectangle is any rectangle which has side small l here and big L here, such that the ratio is equal to golden number. So now I take 3 orthogonal triple of golden triangle, rectangle, as in the picture, and I look so I use my. If I look at this vertex nu here, so this is the blue rectangle. This rectangle and this rectangle are all golden rectangle. And this side is 1. So this side is 5. And a little bit of geometry shows that the distance from nu, from this vertex, to the 4 other vertices is equal to 1. And why this is true? Because this phi, the golden number, verify the fundamental equation, p squared equal to 1 plus. And from this, you get that the distance from nu to this vertex, and from this to this vertex, and to this vertex, and to this vertex is 1. So which means that we have a piece of the icosahedron. So this is when I complete the construction. With this construction, with this process, we can construct geometrically the icosahedron. In some sense, we have a proof that the icosahedron exists. And now we will be interested by something, is that inside the icosahedron, we have 5 tetrahedron. You have here the different color. And the theory that I'm going to do can be done by tetrahedron or by also 5 octahedron. Here, in this picture here, we have just 1 octahedron. How we construct this? We take the edges of the icosahedron, we take the middle, and we join the middle by segment. So, and then this is what I said, an octahedron can be formed by connecting midpoint of the edges. And actually, we can find 5 octahedron. So this is why at the beginning of my talk, I said that the number 5 will play a very important role, and 5 is the degree of the quintic. And this is from Wikipedia when we put the 5 octahedron. And this is very important for so many reasons. So, and now we have something that we call the lattice E8. The lattice E8 is some lattice in the 8-dimensional real space, and it is very special lattice. It is the set of all the, sorry, here I should put E8. And we ask that the sum of the component is 0 mod 2. And we look at all the shortest vectors, and we have 240 vectors they are given here. So when we have lattice, we can always define what we call the theta function of the lattice, and the theta function of the lattice can be given if we have some lattice L. The theta function is given by the sum over, we consider all the elements of the lattice and exponential, and here we take the norm squared of and tau. And tau here is a complex number of so I put minus here, so I ask this. So this is the sum of this exponential, the exponentials over all the elements of the lattice. And what it is important is that the theta function of this complicated lattice can be written in terms of the 8 powers of the Jacobi theta functions. So I will be back to this later. And we have the connection between the quintic and the E8 lattice through to the icosahedron. And this we will come clear by looking at the theory of singularities. So essentially, the icosahedron acts as bridge between the algebraic problem of solving a quantic and the geometric structure of the E8 lattice. Now, what we are going to do, we are going to take the icosahedron. So it is the most enigmatic Platonic solid, and then we project it on the sphere, the surrounding sphere. And then we use the stereographic projection to go from the sphere to the plane. And now this is our philosophy. So we have the quantic. The general equation of the quantic is something of the form A0 plus A1x plus A2x2 plus A3x3 plus A4x4 plus A5x5. And now it is important. Yeah, I can change, I can normalize. So I change here, and I say I start by A5. So A5, 4, be and one, so we have to say that the general quantic have been solved by Hermit, by Kronecker, and the one who really use geometric idea is Felix Klein. But Brzezinski reduce this general quantic depending on those coefficients to another quantic depending only on one coefficient B. So this B is for Brzezinski. And this B, of course, depending on the coefficients in K. And I have to say that from Galois theory, the solving the Brzezinski form of the quantic is not simpler from the Galois point of view than the general quantic. But from the geometry, this B is important because it has a relation to the icosahedron, to elliptic curves, to the Gordon ratio, and to the E8 lattice.
What does it mean to give a general solution of a quantic?
Sorry?
What does it mean to give a general solution of a quantic?
The general solution. The solution. Because if you have one solution, then you can reduce the quantic to the quartic equation. And
okay. So when you have a solution, then you have a quartic, and then you have a solution by radicals. And the quintic itself is not a solution by radicals. No, not in general.
So here the link between the geometry and the algebra. Assume that we have a group. When we have a group acting, for instance, a group of matrices acting on C2. If we have a group G active on C2, for instance, we are interested in the orbifold C2 or G. And one way, what happened? One way to understand this geometric object is to look at the ring of polynomial and then and we look at the ring of polynomial invariant by the group. We can act, we can, if we have an action of G on C2, we can transfer its action to on the ring of the polynomial in Z1 and Z2. And now it is a theorem that this ring of polynomial is generated by three invariant polynomial. And these three invariant polynomial verify some relation. And this is one of the main points in the theory in invariant. I have to say that the theory of invariant was the big theory in the 19th century. And even more, they transformed completely the projective geometry by using invariant theory. And then For instance, if I take the cyclic group C4, this is the cyclic group, and I look at the ring of polynomial, and then I look at all the ring of polynomial invariant over C4, we obtain that this ring of polynomial is given by C of X. So this ring of polynomial is also C4, Y4, X4, XY. And then from here, you see that can be written as the ring of polynomial XY here, and now Z. And the relation is that if I multiply here, if I have to take the power 4 of this, so X, Y minus Z4. So I take this ring of polynomial in 3 variables, and I divide it by the AD generated by X4 minus Z4.
I have a question. What is SU here?
So
SU2 of C. It says
The cycling.
C is here. Yeah, this is like, I mean, SU is the special unitary group.
special unitary.
Yeah.
So matrices of order 2.
Yeah. So all the groups that we are interested are subgroups of SU, SU2 of C.
I see. And here it seems that the orbifold doesn't depend on the action itself, only depends on the group.
Yeah, because you can define the orbifold. Once you have action of group on C2, when you have action on a group on some set X, you can consider this.
Yes, but here, so it seems that when in the example you have CXY to the C4, and there I don't see any action, and it seems that this does not depend on any particular actions. Can we have several actions of C4 in C, and all of them are going to give us the same orbifold?
Sorry, I don't see. But
Yeah, my question is, can a group give us 2 different actions so that the orbifolds are different?
if the group act on some sets, the orbifold is unique.
Yes, but if you have one group can act in 2 different ways in C.
It depends on the action, of course.
And but it seems that the orbifold will be it doesn't depend on the action.
No, but here the action when I fix the group, I fix the action, and this action is translated on the action on the polynomial.
Yes.
This action is the action that I have here.
Yes.
And then this is given by this, and this depends on the action. If you change the action, you change everything.
Yes. But here we in the example we only have C4. We only know that this is the cyclic group 4. We do not know anything specific about the action.
Because I didn't give you the action. Here, the action. I'm going to give you the action in one. Let me see if it is written. So, for instance, here we have different groups. We have the cyclic group Cn. So this is for n equal to 4. It was here for n equal to 4. And this is for cyclic group any. I really don't see the question actually. You have an action.
Yes.
And then you look at the invariants.
Yes.
And the invariant. The group of the invariant is generated by 3 polynomial invariants modulo a sum relation.
Yes. My question is just that that I do not know what is the action of C4 on this ring of polynomials.
Yeah.
I do not know what action is that.
the action is, this is the, how to say. If you have set X, and then here you have a group, and the action.
Yes. Yeah, I know, but I don't know. What I don't know is what is the particular action of C4 on CXY? How is this acting? How is C4 acting on this ring of polynomials?
How C4 as so we have let me see. If you have let me try to find a way to explain this. C4 is, let's see. If I have
It just is it the multiplication by I?
no, it is more. I'm trying to find a way. So the Cn here, I look at it as I look at all the subgroups of SO3, the matrices. So it is, I look the subgroups, we have classification of the finite subgroups of SO3. And you have the cyclic, the tetrahedral. So this is cyclic. So cyclic group is generated by, I look at it as exponential to I pi over 4. And so I look at it as matrix.
Right.
So here I have exponential to I pi over 4.
Yes.
Here 0, and here 0, and here exponential minus 2 I pi over 4. So if I have a polynomial, X and Y, I look at it as a vector, and I act on it on this matrix.
Yeah.
I don't look at Z4 as just an algebraic group, Z over 4.
Yeah, I see.
So this comes from the classification of finite subgroups of SO3.
I see. Thank you. Thank you.
So it was, how to say, I have to use this classification of finite subgroups of SO3. And we don't have so many. We have the,
You were a little bit too quick.
Sorry.
We did not follow very well the last part of your.
Yeah, this is, for instance, here, it is written here that SE2 is considered as S3 and it is subgroup of SL2 of C. It is coming now. So this is here, I use the fact that the subgroups, the finite subgroups are given here. Cn and the dihedral group, trihedral group, and octahedral group, and isomedral group. And the relation for each one of them is given by this. So the group of polynomial invariant is generated by X, Y, Z, and for each one of them, I have the relation. I have to consider, so if I wanted to, or before T2 divided by one of those groups, I have to divide the ring of C X, Y, Z, and this is the relation. Is this an answer to your question?
Yes, definitely. Thank you.
So we have to wait just a little bit to it is coming from. So here what I said, when 5 is the most important number for us because of those three isomorphisms. Here I have to say what is gamma of 5. Gamma of 5. So SL2 of Z is the ring of the matrices with coefficient in Z with determinant 1. This is the modular group, and inside this modular group, I have what I call gamma of 5, and gamma of 5 is the set of all the matrices SL2 of Z, and which has congruent to the identity mod 5. So this gamma of 5 is very interesting, and because also if we look at PSL2 of 5, the group of matrices 2 by 2 with coefficient in F5, it is isomorphic to A5, and A5 is the group of even permutation of 5 elements. So it is a finite group, and it is a group of order 60. A group of permutation of 5 elements is of order 120, and this is the middle, the half. And this isomorphism is really the fundamental isomorphism. SL2 of Z divided by the subgroup gamma of 5 is isomorphic to SL2 of 2 F5 and isomorphic to A5. So we have this kind of isomorphism, and it is also related to the quaternion. We have the definition of the quaternion here. Is this? We have the law of multiplication of quaternions is we have 3 elements.
Your computer has a soul, I think.
And the multiplication is done like this: A, I, J, K, J, K is I, and Ki is J, and if we look at the other signs, we have minus a sign. So if we look at this, and then we can look at, and we can define what is the norm of a quaternion is just x2 plus y2 plus z2 plus t2. And if we look at the quaternion of a unit norm, we obtain SU2, the same SU2. We have many ways of to read what is this group SU2. And we have that the group of icosyon is that the inverse image by the covariant map pi of this A5, the group of even permutation of 5 elements. So the group of the icosyon, which is G, is related to just the group of permutation of 5 elements, which is a geometric things, because the icosyon has many symmetries. So I go, and the icosahedral group can be written in terms of quaternions by this relation, and one more, you see that square root of 5 appear. So the group of the icosahedron can be written also in terms of quaternion, like this one. So here, as I wrote, the relation between the group of invariant of the finite groups, and this time I call them V, F, and E. Because for the icosahedron, what is important are the face, the edges, and the vertices. And now if we look at when we have the icosahedron, I project it on the sphere, and then by stereographic projection on the plane, so I can look at the polynomials vanishing at the center, or the middle of the edges, or the vertices. And this is what we call Klein forms, which is Felix Klein who did this, who found the polynomial V for vertices, F for faces, and E for the edges. And this beautiful relation that we have between F, E, and V is not trivial at all. Because the number 1728 can be found also in another theory, in the theory of Eisenstein series and modular forms. We have the same form and the same number. In any case, F is of degree 20, and F3 is degree 60, and V is of degree 12, and V5 is degree 60, which means that this expression is of degree 0. And now I go why I said before that inside the icosahedron, we have 5 inscribed octahedron. And now the octahedron is inside, then we can look at this polynomial. And from this O1, we define OI, we define 4 other polynomials just by acting by the notation given by U and V. So from this polynomial OI, we can construct 4 others, and we have 5 OI. And we had before V and E, so I can define this XI. So this XI are degree 0 in X and Y. And so they are rational functions. Now, if Z describes the icosahedron, then we will have a permutation. We will have the action by A5, which is the group of even permutation of 5 elements. Here, another something completely different come in this program. This is a letter from Ramanujan to Hardy. Hardy wrote, let me write just the relation 5 in some more complete way. Actually, this is letter in 1912 to Hardy, and also submitted as question 352 in the Journal of Indian Mathematical Society. So this relation 5 says that this continued fraction, and then I take 1 plus e minus 2 pi, 1 plus e minus 2 pi, and so on. So this continued fraction is given by the Gordon number.
But it's not the one that is written by Ramanujan.
This is not the one. Let me take my notes because E minus 4 minus 6. Here minus 2 minus 4 minus 6.
Yeah.
And it is given by, here we have root of 5 plus root of 5 divided by 2. And then minus root of 5 divided by 2. And then we have fifth root of 2. Now this is just magic equation. Y pi, which is a number related to constant number. And there are a lot of stories about this equation because when Hardy received this letter, he stopped to talk by admiration of this formula. And he asked Ramanujan to give a proof, but proof was given by.
So in this 4, 5, 6, 7 are a list of theorems that Ramanujan wrote to Hardy. Each one of them is a theorem.
Each one of them is a big theorem. Yeah, yeah. And this is just a piece of the letter. I have the letter.
No. Okay. You receive a letter like that, and then I have a lot of work to do.
So this formula will to understand this formula with modern terms, we consider a power series G of Q given by this series here. And we can write it, if we don't like series, we can write it as infinite product. And if we like to have a geometric function, we can write it in terms of the geometric function. And you see one more 1728 appearing here. So this 1728 appear in the invariant theory, in modular forms, and in completely different topics. If you add this function g of k, you go to the function h. And here h is given in series, infinite product, hypergeometric function, another formulation of the hypergeometric function, but this is not so strong because we have a lot of relationship between the hypergeometric function, but still we have this 1728 here. And now another big function, the Ditkin eta function, one of the fundamental functions in mathematics. It is given by this infinite product. And of course, implicitly, this tau, q here, is just exponential up to I pi tau, and implicitly, I assume that imaginary part of tau is a positive number. What is important here is the upper half plane. This tau is here. So when we have these three functions, we can define R of Q. And this R of Q has this expansion. And you take Q is equal to some value. If you take this Q, if you take Q is this number, or the inverse of this number, if you bring this number here, you obtain this continuous function here. So Q is, we have just to take Q is equal to exponential minus 2 pi. And the continued fraction of Ramanujan can have this form. So what is important is that this is the Ramanujan. This number here is this number. The value at exponential minus 2 pi. But more important, another revolutionary formula is that the fifth power of 1 over r minus the fifth power of r is given by the sixth power of eta function. This means that we can do something with it. And this is theorem of Duke of recent theorem 205. That if I consider the upper half line and I act on it, when we have the upper half line, we have an action of the modular group on it. And if I take a matrix 2 by 2 with determinant 1 with a coefficient in Z, and if I take Z here, and I act on it by CZ plus D, and I find something that also of imaginary part positive number. So I have an action of SL2 on H, and later we will be interested in the quotient of H by SL2 on Z. But here we take just the action of SPSL2, and of course what is important here is that if I change this ABCD into the minus A minus B minus C minus D, I don't change this quantity here. So which means that actually what we have is this action here. PSL2 is SL2 divided by plus or minus 1. And then we can consider the action of F5. And what is important is that the theorem of Duke is that we have a contravariant action, which means that you can consider PSL2 acting on H. So this is H, what I call H star in my paper. And then here we have the action. Here we have S2. And here we have the action of the group of the icosaedral. And S2, we have this H here, this is bi-holomorphic. I forget some point, some compactification point is bi-holomorphic to C, which is S2. So we have here the action by the group PSL2 of F5. And here we have the action by this. Here we have this isomorphism that it is given by the typology, the modular function. So that I can go here or here or here. This diagram is commutative. And the R is the one that gives. This R is the one that gives this kind of isomorphism. R is here. Sorry, I call it G, but it is R. So this is a non-trivial theorem. And it's related. So I would like just to go slowly to the end. And here another piece. Another piece, this is what we call the Gauss pair. Gauss, and if for those who read Latin, you see what he wrote. What Gauss did is that consider two numbers, A and B, and B, then define E1, E0 plus B0 divided by 2 of positive numbers. And B1 is root of A0 and B0. And continue like that. What happens is that this sequence and this sequence both converge to the same number. This is what we call the EGM of A and B, the arithmetic geometric mean of A and B. And one of the big discovery of Gauss is that if I take A equal to root of 2 and B equal to 1, and I do this construction, I obtain that the EGM of root of 2 and 1 is equal to 2 over omega, and omega is the length of the Lewis state. Which means that this omega for the linear state is the number pi for the circle. So this is a big discovery because it created a lot of theories before, and this is one of the motivation because I did some work on the linear scale and on how I got interested in this topic. So this omega is given by the formula. Omega is given by the formula minus 1 dt over root of 1 minus t4. And this is similar in the classical circular geometry to that this is 1 minus t2 given by 2 pi or something. So this is big discovery of Gauss, as many other discovery. And now we arrive to the end of this picture, because we want to understand the B of Briowski. We take a general quintic, we write it in Briowski form, and we want this B. We have, from this B, we want to construct the roots. And now here, so for each complex number B, I can construct this equation. So I have this B. You see here, we have to read what is this. This is considered as period. Period, because geometrically when we go make the tour, we have a period. This is period, and this is period. So from this B, we can construct the period by the arithmetic geometric mean. So we have this stuff. I said the arithmetic geometric mean was constructed for two numbers, but it was expanded to the complex number by the algebraic geometers. So we have the arithmetic geometric mean even for complex case. Then we can construct this tau. This tau is in upper half plane. Tau gamma of 5, which is a subgroup of SL2, and when we take the quotient of the upper half plane by gamma of 5, I obtain something over the H plane divided by SL2. And here in this upper half plane, in this quotient, I have the action of PSL2 of Z over 5Z, which is what I call FZ. And here we have the function R of Ramanujan, discontinued fraction. It is really remarkable that something written 100 years before they wrote here. And here we arrive at the sphere and inside we have the icosahedron. And then we have the action of the group, the icosahedral group here. This icosahedral group here, we have the three polynomials of Klein for the vertices, for the faces, and for the edges. And from here, we can define what I called before xi. And this xi was constructed by considering the 5 octahedral inside. And then here, so what I call the octahedral function. And then we have the action of E5. We have 5 octahedral inside the icosahedron, and then we can, there is some kind of, we can make permutation by acting by the group E5. So this is the program. And then we obtain, when we have this icosahedral function, we can check that the xi are solution of this equation. So this would be, we have to make the tour to go here, and then we obtain xi, and the xi are there. So here I have to say that there is link in my title. I said that there is link to some special Lie algebra. This is and the Toric varieties. And this is coming from the R relation. We say that if you take a group acting on the plane, you can act on the polynomials. This group of invariant is generated by 3 polynomials up to some relation. This relation from the geometry is important, and because it has some singularities, and we have to describe the singularities of this. And more than that, in this relation, if you take any relation, for instance, one of them, you have action of the torus. If you take, for instance, xn plus y z, you have the action of the torus on it. The torus is just a C star. So with it, they are what we call Toric varieties. Now that we have, we can define this action, and we have the classification with this, and this is how Lie algebra appears. So I wanted to just finish by a small arithmetic problem, and to show another way how Lie algebra appears. And here I have small arithmetic problem. Find positive integers p, q, r such that 1 over p plus 1 over q plus 1 over r greater than 1. And the solution you have all done here. P equal to 1, and then you take q and r any positive integers. You take p equal to 2 and q equal to 2, and then r is any, or 2, 3, 3, or 2, 3, 4, or 2, 3, 5. And then I will represent the solution in the form of some y. But be careful, I'm taking p minus 1.
I do not understand what are the asterisk, any one that we want.
Any number.
Any number.
Yeah. Any number. Because you have already.
Yeah, of course, yes.
I put this solution in the form of something y. But be careful here, I take p minus 1, q minus 1, and r minus 1. Insert that p minus 1 plus q minus 1 plus r minus 1 plus 1 is equal to p plus q plus r minus 2. And for instance, if here, I see happening what we call Dinkin diagram in particular case. Here, when p is equal to 1, p minus 1 is 0. So I don't have this branch. So I have, in some sense, one line. This is why it is written here. And this dot here representing the end that I have. If p is equal to 2, so if p is equal to 2, I have only one circle. And this is why I have here, and here, and here, and here. So this is what we call ADE diagrams. And these ADE diagrams, I know at least 12 domains in mathematics where this ADE diagram appears. And also they are related to true representation theory, to the subgroups of the tetrahedron, icosahedron, and so on. So what is the conclusion is this, and this is due to John Mackay in 1980, that the resolution graphs of C2 of G, what I call C2 of G, is the orbifold. So let me go back to this. It is given by and what is this R is when we consider the invariant group, we find that it is given by 3 invariant polynomials, and they divide by a relation polynomial. So geometrically, represented by the 0 set of some polynomial in 2 variables. And this 0 set, some kind can have complicated singularities, and then we have. And what Mackay observed that the finite group of SE2, or if you want, the Hamiltonian of norm 1, it is related to this kind of diagram, Dinkin diagrams, and it is related to the singularities of this hypersurface. So here we have this, and now I want just to finish the relation. I started by showing the Dick diagram when we looked at this Quintic, and we saw that the coefficient of the power series expansion is given by Dick by Catalan numbers, and it was our first time that we meet graph theory. Another possibility to see graph theory is we take a graph. I take a graph, and I assume that this graph has no loops or mid-edges. I don't assume this, I don't assume this. And then I consider this matrix with 0 and 1, which is what we call the adjacent matrix. And we have small theorem, but it is very nice because we have actually equivalence. The largest eigenvalue of the adjacent matrix is less than 2. This means that 2i minus the adjacent matrix is positive definite. This means that the graph is isomorphic to AD. And I think I don't have time to speak about ER as zeta function and the link of it, so I will stop here.
Okay, it's time for questions. If there are someone that is following on Zoom and you want to make a question, or someone in the room. Peter?
I was just curious, the McKay that you're referring to, is it the graph theorist, Brendan
Yes.
McKay?
John McKay.
John McKay.
Yeah. McKay, he really did. So when we consider the upper half plane and we divide it by SL2 Z, there is what we would call the modular function, which gives the isomorphism between them. So, and this function has some expansion of power series. So we have here 1 over 2, and here we have some coefficients. And what observed John McKay is that those coefficients are not arbitrary. They have interpretation of some special Lie algebra. This is the big story of John. He made a lot of deep observation. It's not only it. And he is one of the, how to say, not the creator, but the discoverer of this, what we call the monster. This big.
It's not.
So there are so many things to say here, but I think it's for today's.
So let me ask you a question. In this diagram in which you showed us the whole program, in which you have all the different realms and their connections, there was one question going from the coefficient B up.
Yeah.
Right. Do you have an answer to that?
No, this is,
Can we see the
just
diagram?
in way of talking to things, not an open question.
Ah, okay.
Yeah, this is how to write the solution from yeah. You go from P, you take P, and then you apply some algorithm.
I see, I understand.
You go to tau, and then you go back to this, and you go back, and then you apply the Ramanujan function.
Yes.
And then you arrive to the icosahedron and the octahedron. And then from here you construct the xy, x1, x2, x5. Then you have the x8. Then there are the solution
I see.
of the quantic.
Of that.
And then this B is given by the symmetric function.
I see.
Yes.
So you've given us essentially an algorithm for extracting the solutions of the quintic from the Ryoshki form.
Yes.
Does it depend on the quintic being in Ryoshki form? Do we have other similar kinds of algorithms for other normal forms?
Yes, of course. Yeah. There is of course, here I choose to work with the octahedron. Then, this is one of the other miracles of Ramanujan. Ramanujan has another continuous fraction, and you can decide to work with the tetrahedron also, and then you have another program. And of course, this Brioski form, it has the advantage of depending only on one B. But you have the solution given by Felix Klein. But this one is independent from Brioski. But then you have to use elliptic function and hypergeometric functions. And Hermit also saw that here you have to use the theory of division in elliptic function theory. So there are a lot of solutions. What I like in this is to use this Ramanujan.
Is there any connection between Golden ratio and the golden,
golden ratio, and
this golden number you're talking about.
this is the same.
It's the same.
It's the same thing.
Same.
It's a ratio number the same.
This is, the golden number, the golden ratio, the golden spiral, the golden. So the point is that this golden number is really deep study.
And I was asking this is because in the problem we solved, the fifth problem, we have like 1 by 1 plus e raised to I 2 pi by, like it's continuing, but everything is like a multiple of e raised to I 2 pi.
Yeah.
But that's actually equal to 1, right? So is that
Sorry. 1 plus.
it's I is also there.
Yeah, no, the eye is not. The eye is missing. The imaginary eye is missing. That's why.
There is no I.
That's why it's not
But this question
because
was also interesting. If you look,
it comes to the golden ratio.
look
Right.
at the golden ratio.
That's what I
Have
was asking.
Yes. This is right. Yeah.
If I put I there, here I understand there was no I already, but if I put an I there and if I count like each branch, the sum comes to be something like 2, 1 by 2, 2 by 3, 3 by 5, 5 by 8.
Yes.
So the
Yes.
golden
Ratio.
ratio
Yes,
pattern
it does.
comes.
This is what I
Yes.
Yeah, that's
It is written here.
Yeah.
Yes. The golden ratio can be written. This is coming just from instead of writing phi squared equal to minus 5 minus 1 equal to 0, write phi squared equal to 5 plus 1 and divide by phi, and you obtain phi is equal to 1 plus 1 over 5. And then this phi you replace, and then you obtain 1 plus 1 over 1 plus 1 over 5, and you iterate, and you obtain this relation.
why I was confused.
And also all this relation.
Erika ci ha trovato. Il golden ratio è anche il rapporto tra.
No, but what is important is that when you take 1 and 5 here, then you subtract the square, then you obtain this equal to 1 minus 5, which is 5 minus 1, sorry. This is 5 minus 1, and this 5 minus 1 is 5, 2 minus 5 over 5, and this is 1 over 5. So we obtain 1 over 5 here. And then you subtract, and then you can construct sequence of decreasing squares, all of rectangles, all of them are golden rectangles.
Yeah. Historically, if I remember well, historically speaking, the golden ratio appeared for the first time. Rationality of the side and the diagonal of a pentagon, correct?
Yes.
Exactly. Here. And so why you put it in the end rather than in the beginning? Because that is
Because this, I'm not using this mainly. Well, this was just to show that.
no, but the question is there is no connection that go from here to the icosaedron.
There is, but
By the way, there is so this has nothing to do with your talk, it's just a curiosity. There is a historiographic querel about whether the first irrational number that is discovered is the square root of 2 or a golden ratio. It's absolutely not clear which one has been discovered first.
And I found that in a paper of Attia that the Platonic solids were known in Scotland long time before.
Yeah, that's exactly a lot of.
2000 years before.
Scotland?
Yes.
Really?
There are some stones cut. I can send you the reference.
Yeah. You don't have the stones themselves.
The stones you do not send.
No. Just a,
So there can be golden rectangles, golden spirals.
yeah, it's got the spires
The
coming
spiral
from here.
comes from there. Right. Like you can draw the spiral from that
I see.
relation.
Of course, then you have the spiral here.
Scottish had 5 Platonic laws.
Yes. So I can send you the reference.
So exactly, so that a nice question from all that you told us and many other things that I suppose that you could have told that you did not say. There is a way to derive a theorem that Plato's Polyedros are only 5. Why there are only 5?
Yeah, this is.
Plato, you can give a very complicated proof of it that the pure geometrical. So the idea is, can we have an arithmetical proof?
Yes,
Is the theorem?
thus you have to put some axioms. What do you mean by Platonic solids? Then you can.
No, so you can give a proof. And he give a geometrical definition of the Platonic solid. I don't remember exactly which is, but I think it's a question about equilaterality. I don't remember exactly the definition. And the proof is purely geometric. So you have, it's a combinatoric of geometrical connection. Now, I don't remember the proof. But the question is whether you have a pure arithmetical proof, that is unicity theorem.
Rationality of pi. From the rationality of pi.
The rationality of?
Pi.
So what the relation? So the question is, how can you prove
It depends on the
that there are only 5 Platonic solids?
I can give you a proof. Yeah, can give you not now, but I can.
No, I don't want that you give me the proof. But I did not understand the relation between this and the rationality of pi.
Yeah, because it depends on the axioms. What is the definition of Platonic solids? I could put it here, but
The arithmetical definition of Platonic solid. Okay. This is not trivial.
no, it's fine. So it can be done.
Okay.
It is less trivial than the Ramanujan continued function.
Okay. Unity of mathematics. How do you explain
Yeah,
this? How do you
and
explain
this is
that?
why I have to say that we tested here the references. Here we are trying to finish a book using this to compute something that we call the lattice point problem. Compute the number of integral points inside some parallelogram, and we use this kind of similarity.
By the way, can come back? No, here. Jonathan tried to, because Ahmed suggested to invite John Baez. So we got an answer from him. He got an answer from him yesterday. So
Yesterday?
yeah, that he should be able to come in the spring.
Very nice. Very nice.
This spring? No, next spring. Yes.
No, next.
In one year,
26.
20. Oh. So he can be in.
No, but okay.
Okay.
Do you have any other questions? Yes. Ben?
One slide had the 4 tree. branching in 4 directions, one of the later slides. I think one.
No, the infinite 4 tree, complete 4 tree. You had that.
Yeah. Yes. Is this related at all to, I mean, to the golden ratio, or how is this supposed to?
No, this is
Layer.
just 3 of how to say 4 regular 3, and to compute. I wanted to compute the adjacent matrix and the ER zeta function of this tree.
But this tree
But I have to define what is the ER.
is related to the Banach-Tarski paradox.
I see. Okay.
Which I mean here is that for kind of in graph theory, the zeta function can be very simple than classical arithmetic.
Okay, do we have any other questions? Marks? Okay, let's thank Ahmed again.